show. So who we are and what we're doing. In this physical chemistry, we need to model properties of molecules and nanostructures with theory and computation, because it is physical chemistry. And we want to understand what comes out of the characterization experiment. We admit that electron is a wave, and now we know what it does in free space. Now we need to come in the confined region, which models oligomers, right, and confined nanostructures. What is our scientific question? If several people are confined in the elevator, can they avoid interaction with each other? So, in some sense, it is what we are doing. Not in this room, but electrons in our models. If I do have a tennis ball and I smash it into the wall, it will reflect back. If I have a piece of cookie dough, I smash it, it will change its shape. Will electron be like a tennis ball or like a piece of dough?
Tennis ball.
Huh?
Tennis ball.
Let's check. In the free space, it was changing shape. Who knows, will it change shape this time? And if we have a tennis ball, it can approach as close as possible to the wall. Will the electron be able to approach as close as possible to the wall? Or it will start feeling and reflecting like a smart person, pushing the brake before smashing into the wall.
Depends what the charge is.
Exactly. So let's, but now we are looking not at the physics and electrostatics. The charge and electrostatic attraction is when the walls are smooth and it starts feeling it ahead of time. Now we have absolutely sharp wall. It's very similar as we have. And we wonder if it will approach close or it will start reflecting from distance. We will have actually two walls because it is a little simpler. What else? There will be another scientific question that we are going to answer with our computation physical chemistry tools. And the right way to make science or mimic, to pretend that we are doing science, is to put some questions that our curiosity set prompts us, and then prove it right or wrong with some math. Make sense? Okay. So we are starting the third chapter about boxes. Next, our next presentations will be in like about 10 meetings in the middle of the next chapter. So we have like a couple of weeks free of presentations. I don't know if you. So you can skip the stuff here. You have like 2 weeks to do it. Although if someone does it earlier, I'll find a way to reward this credit. And for next Monday, it will be basically make an educated, intelligent run of this script. And we will be doing it on Wednesday night. So in some sort, next homework is a lab report for coming Wednesday night. So it shouldn't be very exhausting. And it sounds like finish. 1, 2 vowels are together. Such revolution. So in here we will illustrate how the electron bumps in one wall and another one and reflects. So in partial it will answer the question that we discussed right now. So last time, I don't remember why I was in a rush. Probably we were doing session on homeworks. So if you have material A and B, A conducts, allows electrons move freely, B is insulator of vacuum, then it is like an elevator where electron, not even several electrons, even one electron is feeling squeezed. And we are going to see which consequences the squeezing, or there are several synonymical words, constraint, confinement, impose on the motion of electron particle. So before in free space, it was able to move in any direction with any speed, no traffic signs. Here, one of our main questions will be other traffic signs. Is it allowed to move with any speed or certain? Then what else? What was minimal possible energy of electron in the free space? Like total energy of rate of Hamiltonian was only kinetic energy, right? Can kinetic energy be negative? No. Can kinetic energy be absolute zero? Yes. In free space. Why? P squared over 2m. If momentum is zero, then the kinetic energy is zero, right? So it can be zero. And now, so it is as a low suit system. You have a precedental system. If in one case it was able to be zero, can it be zero in other cases? I bring you a little warning that it was a rather exotic exception. That there will be something that prevents electron to have zero energy. So when they are like, if I'm squeezed I'm claustrophobic and I'm squeezed in an elevator, I cannot relax. I cannot have zero energy. But it is like hand wavy joke. We need to go over it with math. Next question. How this level of minimal energy, how this extent of analog of claustrophobia for electron depends on size of this box. And here there is a really big science that was feeding. It brought this area of science answering how properties of molecules and nanostructures depend on size where electrons are allowed to move. It brought us industry in like light emitting diodes for quantum dot TVs. A lot of other applications on one hand for everyday common person. And for a big group of scientists, it brought a lot of governmental support to research this stuff. So it's a really simple aspect of many natural objects in chemistry and in physics that can be understood with quite simple concepts. So I think you enjoy it. Color. Please let me know if this equation seems, if you are very familiar with it or you see it for the first time.
Familiar.
Huh?
Familiar.
Can you explain what is it?
The wavelength.
Huh?
The wavelength over electron volts.
But why? Who needs it and why?
For color.
Okay, and who needs color?
Well, it's to like look at your molecule and see what color it's emitting, what its wavelength is. So you know it's electrochemistry almost.
Okay, which color the molecule exhibits? How does it visually appears on transmission or emission?
Emission.
Okay. So if we and what energy of what?
The was it lumen?
You told that you do it like computation. You already, without any preparation, you can already get C in computational chemistry advanced. So you have a background. So Coma and Luma, occupied and unoccupied orbitals, right? So by transmitting electron between them, one absorbs or emits light.
Advance, right?
Mm-hmm. Yeah. So, in part, in this chapter that we are starting right now, we will be dealing with the energy between analogs of orbitals. And by this conversion, we can get the wavelength of color the material emits. So whatever we model with this little box, we will be able to predict at which wavelength it emits. And the question of curiosity is, can one manipulate the color the material emits by changing size of the box? If it is possible, it is a revolution in engineering. Because if you already went through some chemistry, you know that dyes, especially in ancient times, they were like precious, expensive, and there are only few dyes that you can purchase. And there are like very few colors that can be bright emitters. Now we can synthesize, but also not continuous spectrum. And if this thing works, we can continuously provide material of any color for industry, which would be quite appreciated. Or for TVs, which we all use because it is a computerized century. Right? Oh, someone in the chat. Check. Spencer has a question. How did you get 1242, or it is just standard for finding the wavelengths of color? Spencer, I'm very happy to have discussion. It's I was missing this part. So this is conversion factor. So all units and all system of units for like energy and wavelengths are designed by humans for humans. And where this conversion factor nanometer times electron volt comes from, I believe I can tell you a little bit more. So when we were, so what I'm going to answer will not help any of us in practical life. It only satisfies the curiosity. But at the very beginning, like meeting number 2 or 3, we had an equation which looks either this way, or it looks lambda times 1 over here equals when we can use letter C or V for velocity. So when we do have a wave which is periodic in space and in time, the period in time is t, period in space is lambda, and if it is already existing traveling wave, when we were deriving wave equation and making derivatives, we found that distance over time is velocity, right? So in some and on one hand. On another hand, 1 over time is frequency, and we will go over it again and again. Frequency times Planck constant is energy. Make sense? So by converting this equation, by converting frequency into energy, one gets lambda times energy, gives this factor, which is related to the speed of light after molecule emits wave. Spencer, does it make sense? Or to give some hint? Okay, yeah, thank you. I'm very happy. The discussion is the best way of interaction. So here just little illustration that one of the students in my previous courses did in computation course, and then it was published as peer-reviewed thing. But here I need only a small part of his work. So he made an atomistic model of silicon, which is semiconductor, surrounded by silicon dioxide, which is like sand insulated. So here is the dioxide, here is the silicon, and here the interface. If one explores electronic states and charge density where electrons are, both HOMOS and LUMOS, are very much localized on silicon. They do not want to go into silicon dioxide. So it's just illustration of confinement. So these gray clouds are electrons. And if one does literal computation in order to make electron to avoid this confined space and go to here, one needs to excite it with hard UV of 8 electron volts, which will be like 150 nanometers, which we typically do not use in our regular things. Now, I want to be very convincing. If I take number 8 in electron volts and turn by 90 degrees, it will become an infinity. Convincing? Very much. It's pure math and geometry. Therefore, in all subsequent considerations, we will assume that it takes infinite energy for electron to avoid this trap. I don't have any better argument. It's just an approximation. And here is another thing other student did. This didn't came yet to the part of publication. It's modern materials, so-called lead halide perovskite, with like leads, bromines, encaged in organic ligands. And this blue clouds show that electrons also want to be inside the confined area. So this is possible for oligomers and for such non-structured semiconductors. So I think this should be the last slide from our meeting number 15, and actual lecture will start in a minute. So in order to practice time-independent Schrödinger equation, we do need operator of energy. Operator of energy is summation of kinetic and potential energy. Before, we didn't have any potential energy. Our potential energy was 0. And our kinetic energy is the same in anything we do. So T is kinetic, the second derivative of space, and potential needs to match the molecule or material that we are describing. So right now, we just set up that our potential will be 0 when x is between origin and size of the box from 0 to L and infinity elsewhere, which means that we will have absolutely 0 probability for wave function squared to exist outside of the box. So we will confine our interest in our mathematical derivations only for this limited range of space. So in narrow sense, we do need to solve this equation for this operator H, or potential is this infinite square law. Okay. And since the potential is infinite, probability is 0, and it is 0 everywhere outside of the box, then what it is on the literally at the point where it goes infinite sharp, it's good to assume that already there at the border wave function with 0 and with L will be 0. And if you or some of you are in differential equations, one could tell that it is standard boundary conditions problem. So first one finds general solution, then one matches only those subfamily of solution which match boundary conditions. A little thing that if you're not curious in math, you can just close your eyes and back and relax for me. So generally, solution of ordinarily linear differential equations are exponentials. And if I literally plug in wave function in this form of e to alpha z, where z is my direction, I don't know why I like letter Z better than X today. One can plug in the Hamiltonian, which is only kinetic energy inside the box. Extract all constants, and then identify that the best match between our notations and our guess will be if our unknown coefficients in front of Z will be imaginary. So it is all provable, and if you want, you can literally go line by line. But this just comes from the nature of equation. So then, general solution for this equation, which is nothing but second derivative, right? Second derivative equals function. Second derivative of function equals function, plus boundary conditions. Then general solution will be plane waves. IKZ minus IKZ. Same as for the plane wave. And the only thing if we wouldn't be physical chemists, if you would just do it as an exercise for a math course, one can say, oh, look here, I have solved the equation. Yes, but it didn't match the boundary conditions. It's incomplete solution. It's too general. So, and just by the nature of solving such equations, it's not single exponential, but superposition principle. Summation of solutions is a solution. So we need to add together these solutions with some coefficients, unknown coefficients. And the solution will be adequate, accepted, only for specific values of these coefficients. If you have plus exponential and minus exponential, we can call them C plus C minus coefficients. So we need to set up these equations based on the boundary conditions. And I hope it will be shown. No, it will not be shown. I will just declare it. Who was our best friend in first 5 meetings in this class? Not among alive people, but among the thinkers of the past.
Schrödinger?
Schrödinger is our new friend from just 20th century.
Newton?
Huh?
Newton?
About the time of Newton, but Newton was more like philosopher and physical, natural scientist, more on mathematical trigonometry thing. His last name starts with E. And somewhere on the slides, his name is declared.
Euler?
Exactly. Yeah, thank you. You are deserving some sort of plus point.
There you go.
So, wherever we see imaginary exponential, we can replace it by cosine of this and is letter Z. Cosine KZ, sine KZ with imaginary thing here. Where I do have minus, I have cosine minus I sine, because as soon as we make conjugation, we flip sine in front of imaginary unit. So if we combine terms, then we can avoid imaginary exponentials that some people who do not know Euler take, and formulate this question as C plus C minus cosine KZ I C plus minus C minus sine KZ. So I told you nothing. It is absolutely the same problem. It's just reordering terms. And I just suggested this style of thinking will be a little bit easier for processing. But there were no new scientific ideas. Hallelujah. You guys solved it in your previous homework. You remember? Okay, so the question was to so we set up wave functions a sine alpha x plus b cosine beta x, and we practice to match it to the boundary conditions. This looks similar to previous slide. The only thing that it is x instead of z, it is alpha instead of k. The coefficients here are alpha and beta by some way are different. And instead of b, we have c plus plus c minus. Instead of a, we have c plus minus c minus, right? But other than that, you already solved it. And by matching these conditions, we found that stuff in front of just plugging in argument equals 0 and one gets the coefficient b equals 0. B is the stuff in front of the sign. So, so c plus plus c minus will be 0, which means c plus equals minus c minus. And it already helps to solve it. And then if they are equal by absolute value and opposite by sign, one can replace this one by just by 2c plus, and so forth with the c plus. Okay, what were you doing further in the homework? Then you were finding this phase of oscillations, how dense or sparse are fringes. So if all the signs survive, one plugs in independent argument equals border of the box, and then one finds when the sign at which arguments, at which values of this phase coefficient, sign equals 0. So sign equals 0 when everything inside this brackets equals pi times natural number. So alpha times or whatever phase times size of the box times pi times natural number, which means the phase, which we will call k right now, is natural number pi divided by size of the box. And then we plug it in and get this solution of time independent Schrödinger equation for the element confined in the box. Period. And here are some things that I was mumbling when we just met today. So can it be 0? And how does it depend on the size of the box? So based on the schedule from the previous year, I'm planning to finish this meeting in maybe 4 slides. So if you are thinking that let's wait until something serious will start, all serious things are already behind. You're starting to take notes too late. So here is the solution that we just discussed. So if I know that I'm not very reliable in notations today. I was flipping between z and x, but let's call it just position independent argument. So solution is sine of independent argument times this phase coefficient, which is pi natural number divided by size of the box. And then this 1 over square root of L originates from normalization that I believe we were discussing also during the homework. So because wave function squared and the integrated must give 1. So if we place this coefficient up front, then after making square and integration, one will get 1. How can one call this place? Well, some people call them wave vector. And if we bring up the definition of momentum, which will be this wave vector times Planck constant, then one can plug it into the definition of kinetic energy, right? Which is momentum squared over 2 masses. So by plugging this stuff into here, Planck constant, wave vector squared, 2 masses. And if I replace this wave vector by this by natural size of the box, then one is getting Planck constant squared over 2 masses constants, pi squared, and then number of the solution. So it's integer number. It's discrete. It can be 1/2 or 3/2. Divide by L squared. So let's, I'm going to flip back and check which question I was asking to myself, or which questions you were asking to yourself, or we were asking to each other. What is a minimal energy of electron in the box? And how does it depend on the size? So can minimal energy be 0, or it will be bigger than 0? And if we know, if we have a way to find this lowest possible energy, how would it depend on the size of the box? Right? Now let's work on the derivation that we just completed. So if I plug the integer n equals 1, there will be Planck constant squared masses, pi squared, L squared. So this is the lowest possible energy for electron which is confined in a box. And we were discussing box is either a oligomer or some semiconductor nanoparticle. So is it equal 0? Can you say that this is 0? Is it smaller or bigger than 0? Larger. When it approaches 0, what should we do with the size of the box to make it 0?
Zero.
Yes. So if we pull the walls, like make it from the room, make it a big stadium, or just city, or remove the walls so that they are so far that we do not see them, it will be as good as free space. And the lowest energy will be close to 0. But as soon as we bring the walls closer, this energy grows as 1 over L squared. Do you think it's complicated? But people were getting Nobel Prizes like 20 years ago just for this equation. It just the particle in the box, Louis Bruce is the name of the scientist from Columbia. So the particle in the box problem was practiced and solved for generations of students and scientists in classes, starting from like 1930. And then, very recently, when we all were already born, one did realize that there are chemical synthetic ways to control the size of the oligomers or control the size of the semiconductor nanostructures, and they indeed show like a rainbow of possible colors. And just by practicing this equation with some little additions, one was able to explain this interesting phenomenon. So if someone asks you what is nanoscience, you can say it is 1 over L squared. Nano means small. So one can make standard objects, one can control properties by controlling size and focus. And this all just comes from this equation. I don't know why I'm playing this kindergarten. Maybe previous years I was contriving to set up a surprise quiz in next meeting. I don't remember, but it's quite silly to memorize this equation because everyone can rederive in 3 minutes. But if there is only 1 minute for the quiz, when you do not have time to to rederive it, here are the factors. So 1 over L squared is dependence on size. N squared is dependence on the number of solution. So interestingly, energy offsets and energy levels, again, it's boring equations, but there is a physical chemistry science behind it. It is related, energy is related to momentum, right? It will be like traffic signs. So electrons only with certain momentum and certain energy are allowed to exist inside the box. Not everything, not any electron. If it moves too quick or too slow, no. Stay away from our box. So it is allowed only if there is a certain integer, which we call quantum number. And interestingly, that the energies grow quadratically. So this energy levels will be offset bigger, 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 bigger. And one can also find some useful industrial consequences of it. So offset spacing of energy levels. Now, 1 over mass. This is not a big surprise. Kinetic energy is inversely proportional to mass inertia. If instead of electron, we want to put like a proton in a box, the mass will be like about 2,000 times bigger, and offset of energy levels will be 2,000 times smaller. Right? And here is just combination of fundamental constants, Planck constant and phi. So Planck constant means that if we are in the quantum world, if everything we are dealing with is of the order of nanometers, then these rules will be controlling the game. If you will go to the macroscopic objects, then all of this will be a chickpeas. Planck constant is 10 to 6, 10 minus 34 in our regular Joule second units. So these offsets and quantum properties will be not noticed if I want a wave function of a table or stuff like that. Makes sense? I'll try to avoid quizzes, but just in case, you should be ready, right? Just roughly put where is the square, where is the size of the box, where is the mass. Okay. And if we do want to make a connection to the real world, to like oligomers or semiconductors, here I'm just making one step on translating this particle in the box concept into the equations that are immediately applicable to real world. So if we do have conjugated conducting polymer which is infinite, there is a homolomo gap, a fundamental gap. If we do have a chunk of semiconductor, like silicon, heavy, like several pounds piece, that we didn't convert it into microchips, it also has homolomo gap of like known very fundamental gap. And most materials have this. If they are not limited in size, this is the property, intrinsic property of material. Now, if you try to carve, like to make this oligomer shorter and shorter, or if we create nanostructure of silicon smaller and smaller, then in addition to fundamental gap, which is here bulk means there is a quantum contribution. which is literally originates from this quantization. So this equation that we derived in previous slides, it is not the whole story. It is a correction to the band gap energy. So this is how our particle in the box equation is converted for real-world materials. Make sense? And mass here is not literally the mass of electron. It is so-called effective mass, which addresses. Now I'm telling some advanced stories that are not needed for the class. If the electron is interacting with positive ions, they prevent it from moving too quick, and it experiences different inertia compared to what it would feel in the vacuum. And depending on materials, it can be bigger or smaller than mass of electron, about 10 times. So there are some corrections. And if one is doing a research in nanoscience, one of the typical questions like how to find effective mass for certain material. Okay, and here is an example. If why I'm selecting silicon, because all our cell phones and computers are made of it, right? So and you've heard this 90 nanometers chip, 30 nanometers chip, probably. So everything gets smaller and smaller. So if the gap of the bulk silicon is 1.1 electron volt, and then if I create a structure of the size of 2 nanometers, what is nanometer is 10 angstrom. Right? And 1 angstrom is approximately 0.9 angstrom is the distance from what to what? Hydrogen to hydrogen, molecular hydrogen. So atomic bonds are of the typical size of an angstrom, like 1 angstrom, 2 angstrom, maybe 3 maximum, but it is this range. And if one has 2 nanometers, it means like about 10, 20 monatomic layers. Then the gap will move from this value, which will correspond to infrared, to this one, which will be like greenish or yellowish. Okay. And here's just a motivation for industry. If you need bright colors in LED TVs, one can utilize this stuff. Okay, thank you for your curiosity, interest, passions. Looking forward to see you on Wednesday. If you are online, feel free to ask questions or disconnect, whatever you feel reasonable.
Thank you.
Thank you. See you.